Hello, everyone. My name is Ian Fernandez, and today I'd like to take you all on a tour of some of Earth's most extreme environments and highlight how some of the microbes that live in those environments have the potential to help redefine what makes a planet livable. Let me present the following question. If extraterrestrial life existed, how would it look like, do you think? Would it look like this? This? Maybe that. But what if I told you that more than likely it's possible that extraterrestrial life actually looks like this? As alien-like as these look, these are real, non-science fiction microorganisms that actually reside on this planet. These microorganisms are not your typical microorganisms, however. These are called extremophiles. And extremophiles are a subset of microorganisms that come in many different flavors. We have representatives from each of the three domains of life, as you can see here. They thrive in environments that we deem extreme, relatively speaking, because we are human beings and we are not used to such extremes, so to speak, otherwise known as really high highs or really low lows in this context. The following are some characteristics of extremophiles that they exhibit in terms of survivability. They're able to survive and thrive in really high, really low temperatures, pHs, salinity levels, radiation levels, and pressures, just to name some of these properties. And then you have the polyextremophiles that exhibit two or more of these traits. On Earth, multiple types of extreme microbiomes can be found, which are shown in this image. Today, we're going to be going over just a few of the many extreme environments that we can find here. And I'd like to present the concept of analog environments. So this would be an environment that is found on Earth that mirrors the conditions that can be found on a different planet. In this case, I'd like to reference Mars, the red planet, as our closest neighbor and as a site of astrobiological significance because due to its close proximity and signs of water on the planet in the form of subsurface ice or brine, it's likely that life may exist there. So it is the focus of astrobiological research to potentially send some life detection missions to Mars. Analog environments on Earth need to be environments of high radiation. They need to be cold environments. They need to be low pressure environments and CO2 rich environments to mirror what you would see on planet Mars in this case. The first Mars analog environment that I'd like to review is Chile's Atacama Desert. This is one of the driest environments on Earth and home to an unlikely extremophile called Crococcidiopsis. It is unlikely because Crococcidiopsis is a phototrophic microorganism, and it's phototrophic, so it takes its energy from the sun and undergoes photosynthesis. However, it requires certain levels of moisture to undergo successful photosynthesis, so it's able to stay in a dormant kind of metabolic state for long periods of time, and that's why it thrives in environments like these. It's common in both hot and cold deserts. NASA's Perseverance rover is currently exploring Mars in places like Jezero Crater, where environments have similar levels of aridity. And previous laboratory studies were able to test Crococcidiopsis under simulated Martian conditions that involve low pressure, high salinity, and high levels of ultraviolet flux, which this microorganism was able to successfully tolerate and survive in. Another such analog environment is the McMurdo Dry Valleys in Antarctica, which, similar to the Korolev crater on Mars that houses subterranean ice aggregates, you may have species like Rhodococcus, which is found in this area on Earth, be a potential candidate for a species of microbe that could survive on Mars in this context, as it can survive long periods of permafrost and can tolerate extreme cold and extreme dryness. I'd also like to take the discussion past our closest neighbor Mars, and I'd like to redirect attention to Europa, which is an icy moon of Jupiter, another site of astrobiological significance. And it's because this is entirely composed of ice and a subterranean ocean underneath that ice crust. However, when you go further and further into this subterranean ocean, the water temperatures may increase. So this is where you get the analogous environment of the hydrothermal vent systems on Earth, such as the Lost City hydrothermal field in North Atlantic Ocean, and how you have members like Methanosarcina play roles in the nutrient availability of this area, and is something that may be able to tolerate the conditions of the really hot subsurface ocean waters on Europa. Now I'd like to focus on space as an extreme environment. In this case, we have the International Space Station. A previous study has found that Deinococcus radiodurans, the most radiotolerant organism to date, is able to survive on the surface of the ISS for a year at least. And this is very unique because for a year it was pelted with large amounts of solar radiation and dryness from being in space. But this organism can actually survive 5,000 times the radiation levels that humans can tolerate. So why study extreme microbiomes? Well, for one, extreme microbiomes can offer evolutionary insights to kind of piece together that puzzle. Since extremophiles tend to be microbial, we can use their evolution to learn a little bit more about how these adaptabilities arose in extremophiles. We can also use extremophiles in conjunction with other microbial species to foster a healthier environment and reduce pollution. We can exploit certain extremophilic microbes like Thermus aquaticus and utilize some of its proteins or molecular mechanisms to improve our biotechnology with reference to PCR and the thermostable attack polymerase that is able to amplify sequences at a very high temperature. And then lastly, I'd like to point to its potential to redefine habitability of other planets, which can further inform the search for life on other planets and it can benefit space exploration in the long run. So I'll leave you with this, ladies and gentlemen. If life can thrive in Earth's most extreme environments, how might it manifest on worlds we once considered uninhabitable, like Mars? Are we alone in the universe? What else could be out there? I wager that it could be an extremophile microbial community, perhaps. Thank you very much.